his PhD, and then went to Tufts for postdoc in Barcelona and CERN before getting a junior faculty position at Barcelona. And he's going to tell us about some recent work on cosmic domain walls, gravitational waves, and without further ado, please go ahead.
Yeah, thanks for the introduction, and thanks for having me here and for coming to the seminar. Thanks, Matt, for the opportunity to give this talk. So yeah, indeed, I will be talking about some works that I've been doing in recent years with collaborators in Barcelona and at CERN. And it's going to be about gravitational waves. Of course, I will be talking about particle physics motivated gravitational waves, so things that happen in the early universe. And yeah, part of this talk will also be on topological defects as source of gravitational waves. So let me give you a brief menu of what I'm going to talk about. First, I'm going to motivate the interest in gravitational waves, although I don't need to say much to this audience, of course. But I will be reviewing some recent observations on stochastic gravitational wave background. And then I'll talk about a certain type of cosmological sources of gravitational wave, which we think is particularly interesting for particle physics, and the spectrum, the properties of the spectrum of these sources. And then I specify two cosmic domain walls. So for the sake of this talk, I will be focusing on this epoch here of the evolution of the cosmological evolution, in which basically I will assume radiation domination throughout the early universe, where so the Hubble depends on temperature. And we don't really know, of course, what's the maximal temperature that is achieved in this epoch. It can be anywhere from mega electron volts. This is from Big Bang nucleosynthesis, of course, but it can go up to very, very high temperatures, possibly up to 10 to the 16 GeV. So that's going to be the focus of the focus of this talk. And as this picture kind of wants to transmit the message that it's actually a relatively unknown region of cosmological history, in particular new physics, this is what we are most interested in, may be even abundant or dominant before Big Bang nucleosynthesis, as we do not have that many probes, direct or indirect probes of this epoch. Of course, we do have a probe in the case in which this new physics that we may consider here in this epoch comes in the form of a totally dark sector, meaning that it doesn't talk at all to the standard model. And in that case, if it's, for example, a relativistic dark sector, it would leave a relic background of relativistic species, which we can actually probe using cosmological surveys, in particular cosmic microwave background and large-scale structure surveys. We can also probe it, of course, via Big Bang nucleosynthesis, which is also sensitive to the expansion rate at that epoch. Typically, these constraints are rephrased in terms of this parameter delta N effective, which is just the energy density in the new physics sector, dark sector in particular, normalized to the energy density of one neutrino species. So in that case, the most recent bounds that you get is 0.2, most recent because I'm combining here with the new CMB data from ACT and large-scale structure data from DESI. So this constraint you can translate, if you want, into the abundance of a relativistic dark sector in the early universe at some epoch star with temperature T star. So that's just the energy density fraction in this dark sector, and you get basically a bound of the order of 7% or 10%, depending exactly on what data set you take. So we do know that for those sectors that are completely decoupled from the standard model and are relativistic, there is already a relatively strong bound on their abundance in the pre-BBN epoch. There is a different possibility, of course, that the new physics that we may consider in the early universe may couple to the standard model and therefore sufficiently decay to the standard model sufficiently before Big Bang nucleosynthesis. If that happens, then these relic backgrounds would be absent or very small in abundance, and so we would not get any constraint from cosmological surveys on these sectors. And under certain circumstances, of course, there's a class of models that would be also roughly invisible in labs and colliders if this coupling to the standard model are sufficiently weak. So in some sense, in this case, we wouldn't be able to get those strong bounds that we have from cosmology. So one alternative possibility to probe these sectors, which serves as a motivation for this talk, is gravitational waves. Of course, the idea is the following. The idea is that maybe this is not a non-genetic feature, but I will present models that do have these features. Maybe the new physics features some gravitational wave source in the early universe, And those gravitational waves, of course, if produced, they would be freely streaming until today. And so we would be able to observe them in gravitational wave observatories, in particular interferometers or pulsar timing arrays currently. And the way that they would show up in these detectors is in the form of some isotropic background, because it's generated in the very early universe. And as this picture sorts of wants to represent, here basically in the big red circle is the Hubble patch today, and these tiny circles are Hubble patches at early times. If this process occurs in the post-inflationary universe, essentially you have uncorrelated sources in each one of these Hubble patches, and so by looking at this estimate here, again, comparing the maximal correlation length, which is just the, if you want the maximal one, is just the size of the Hubble patch at early times, compared to the Hubble patch today, you get a very large number of independent sources in your Hubble patch today. So basically the signal would look as a isotropically distributed background and stochastic precisely because of these reasons. So in some sense it is similar to the background for photons, but this of course would be for gravitational waves. So that's a bit setting up giving the setup of what I will be talking about. Now here I will be just giving some words about some pros and cons of gravitational wave observations for fundamental physics. Again, some of these statements I will be justifying them later in the talk. So of course, as I just said, potentially these observations can probe scales that are very high, potentially up to this very high temperature of 10 to the 16 GeV. There is a both negative and positive thing is that currently, to the best of our understanding, the standard model does not, the standard model predicts no observable gravitational wave background from the early universe, so there is no process in the standard model, like the phase transitions of the standard model, that would generate an observable gravitational wave signal. That's of course partially negative because it would have been great to have a prediction from the standard model of a gravitational wave background from the early universe. And the way that typically this is twisted around is that, of course, if we were to detect a cosmological gravitational wave background, that would provide evidence for new physics. Okay, that's the positive twist. Of course, there are several competing astrophysical backgrounds, and that's what makes the possibility to actually claim a detection of cosmological background particularly challenging, at least in the observatories that we have that are currently active. Those backgrounds are given by binaries of compact objects. I will show later on a bit of the details of this. As I said, another motivation is that it allows to probe new physics independently of interactions with the standard model. In particular, even a totally dark sector can be probed very much like in other cosmological surveys. And what I was mentioning before, of course, the generation of gravitational wave sources from new physics is non-generic. So it won't be true, of course, that any new physics that you can come out with will have an observable gravitational wave source, but there are some well-motivated possibilities. And of course, at the experimental and observational level, as you know, there is an exciting program with interferometers, LIGO and Virgo in Cadra currently active. There are Pulsar Timing Arrays currently active, and many other experiments, space-based interferometers and ground-based interferometers active in the next 15 to 20 years, hopefully. So this plot from the nanograph collaboration shows the sensitivities to the current and future sensitivities to gravitational wave backgrounds. We are, in this plot, the strength of the gravitational wave signal is represented by the relic abundance, so omega gravitational waves is the energy density fraction, essentially how much of the energy density of the universe today is in gravitational waves. So of course you see these very tiny numbers, much below the abundance of radiation today. You see here the frequency on the lower x-axis of these gravitational waves. In particular, these data points, these are not really data points, but let's take them as data points for now, are those that come from the most recent Pulsar Timing Array observations at the nanohertz to 10 nanohertz frequency range. And interferometers are currently here. This is the O3 bound, the solid sensitivity curve is from O3. And the dashed curves are all from future interferometers. Okay, LISA is this red one, and this is Einstein Telescope and Cosmic Explorer. So to this plot, I added the upper x-axis, where you see the temperature in the early universe that corresponds to these frequencies, under the assumption that the translation is made as follows. So the frequency is related to the Hubble scale at a given temperature, and then you just redshift and you get the frequency today. So that's the frequency of emission, and then you just redshift. So you see the common statement that we are familiar with is that LISA probes kind of electroweak scale and beyond processes. Maybe we are less familiar with the statement that LIGO in Virgo is probing already very high energy scales up to 10 to the 8 GeV and even beyond. And the other common statement that the nanohertz frequency range is probing temperature scales around the QCD crossover. Okay, so these are all kind of known statements, but I just wanted to recap them here. So concerning these, what I call data points, that are not really data points, but these relate to Pulsar timing arrays, and since part of the works that we do today about gravitational wave background is partially motivated by recent observation by Pulsar timing arrays, I thought it's good to basically recap a bit what's happening with this.
Can you sort of return to the previous plot?
Yes.
So this omega gravitational wave. What is omega CMB today? Is 10 to minus what?
So the radiation is 10 to the minus 5, if you want.
10 to minus 5, right. So if all 7% got converted into gravitational waves, you would have seen it.
So there is indeed a bound already, which is basically this line here in this plot that I'm hiding, 10 to the minus 6. This is the bound that comes from delta N effective, if you want.
Right.
That's
the trivial thing.
That's right.
Okay.
So this bound is here. I just cut the plot right where the
So
bound
this is your 7%, precisely.
Exactly.
Right.
This is
You cannot afford to put 7%
precisely
into gravitational waves.
But yeah, exactly.
Right, but this is
Very
not
good.
expected at all.
Okay, good. Indeed. This typically does not present a strong constraints on gravitational wave sources, because typically you don't expect to produce that much gravitational
But the hope
wave.
is you can go much lower.
So
than
you
this
cannot.
naive.
So in fact, you can already. You see that the LIGO constraint already gets
Is
significantly.
better than this naive. Okay.
Exactly. So thanks.
Good,
You're
good.
making
So
one of
there
the
is-
points. You're
right,
making one of
right.
the points.
There
that
is some hope.
Yes. There is hope. Yes. All right, so in terms of Pulsar timing arrays, I won't really give details about the observation, also because I'm not really an expert of the observations themselves, but I just want to give you the idea in the way that I understand it briefly. So of course, what the type of observations that these Pulsar timing arrays do is these are radio telescopes, and they observe just the time of arrivals of pulses from galactic millisecond pulsars. These have been measured for decades now, in some cases, for some pulsars. And of course, the interval between this time of arrivals is known to be extremely regular. This is why these objects are commonly referred as some kind of clock, very precise clocks. So when you have a common process that can affect this time of arrivals, like the passage of the gravitational waves, what you would have is a perturbation on the geodesics of these photons, of the pulses, and therefore this would induce a time-varying this typically, the way it's seen is the time-varying redshift of the pulse frequency, but I mean, just what one can just think intuitively is just that, of course, by perturbing the geodesic, you will change the time of arrival, you will perturb the time of arrival slightly. And so since this object, the time intervals are typically extremely regular, you can detect very tiny deviations in the time of arrival, such as those that can be induced by gravitational waves. Okay, that's just a general idea. The most recent data from Pulsar timing arrays are, at least from two of the most important collaborations, are given here. So you see, these are the data from Nanograv 15. That's, of course, a collection of radio telescopes in North America, whereas this is the European Pulsar timing array data. And again, this is the excess timing delay. So this is precisely the excess in the time of arrivals in seconds. So you see that the numbers are microseconds below. So again, the period of these things is millisecond, and you're measuring these very tiny deviations in the time of arrivals. So you see, basically, I mean, I don't know if this plot is probably not so, I mean, it just makes it clear that what these collaborations are seeing is an excess in timing delay that can be then fit via power law, or you can also do more complicated models. I will show later what the results for the power law are. The plot that I'm not showing is the evidence that these collaborations currently have that this common process is actually due to gravitational waves. That this is, of course, not enough to claim evidence for gravitational waves. You need also to detect the particular pattern of correlations of gravitational waves, which is commonly referred to as Hellingsdowns. Okay, I'm not showing it here just because it's not the main focus of the talk. But the result from the collaboration is that currently there is a claim to be a 3 to 4 sigma evidence for those correlations against for example, if you look at other possible correlation, the Hellingsdowns is the most favored one currently. So currently I would say there is an excess seen in many detectors, in many gravitational wave, in many pulsar timing arrays. By the way, not only these two, but also the Australian pulsar timing array, the Chinese pulsar timing array, and Meerkat. So the excess is seen. Now the nature, whether it's gravitational waves or not, is at this level in these two observatories, and to a lesser extent in these other observatories. So we will still have to wait for future updates, but I guess this provides strong motivation to focus on stochastic gravitational wave backgrounds nowadays, since there are observations that hint at their presence. So this is what I promised before. This is a power law plot. So basically these are posteriors. The amplitude A and gamma is the spectral shape of a given quantity that I will not report here. I'm just using the quantities that astrophysicists typically use to present these results. The ones that we're interested in are actually plotted in the upper x-axis. There's the spectral index of omega, and the amplitude of omega gravitational waves can be translated from the y-axis by just looking at this formula here. So you get that the current posteriors of the different experiments suggest a background at the level of 10 to the minus 8, so also of similar magnitude to the bound from LIGO, if you want, but totally different frequency. And the spectral shape of the signal, if you look at this as a power law, the spectral shape is kind of a rising part of is a rising power law, although even a flat shape is marginally allowed by some of the observatories, some of the measurements. Okay, so we should think of this as a hint that this should be the shape of the spectrum. Although I also think that these shapes may change, even importantly in the future.
So you see a factor of 10 less than you should, according to our astronomy friends?
A factor of 10 less? Where did you?
I just looked at the graph. Vanilla.
No, the vanilla. So sorry, the vanilla astro prediction here is a vertical line.
It does not give the amplitude.
Exactly.
Oh, it only gives. But
exactly.
Don't they have some rough idea? I thought that you are seeing slightly more than you should. Right,
so
but because you do not put a point on this vertical line.
I decided not to put any any specific.
But do I remember correctly? We see like a factor of 2 or 3 more than vanilla.
I think so.
Or even
Correct?
more,
Yeah.
or even more, depending on the specific model or assumptions that are behind. I can show you maybe. I have some slides.
No, don't bother, because people are saying 2 or 3 more than we should.
Yes, I can show you some extended plots of the types that PTA collaborations show. But I would say that given the large astrophysical uncertainties on the distributions and population of these supermassive black hole binaries,
somehow you trust power law more than you trust the amplitude.
Okay, let me clarify on this vanilla. Let me clarify why vanilla is here. Vanilla refers precisely to what I wrote here, that this is the prediction that comes from supermassive black hole binaries that are in circular orbits and whose evolution is driven by gravitational wave emission. Now, this is vanilla because nowadays, of course, it's understood that there are other effects that can cause deviations from this. For example, the evolution may be initially driven by environmental effects surrounding the supermassive black holes. And also the orbits may have some ellipticity and so on and so forth. So actually, if you look at the zoo of astrophysical models and prediction for the gravitational spectrum, typically there are turnovers at low frequency. So typically it's not just a power law that fits the whole nanohertz frequency range. Typically people think of broken power law that is suppressed at low frequency and less so at high frequencies. And this is all due to the properties, to the astrophysical properties of the system that you are considering. But there is so much uncertainty on this that even the prediction for the slope of the spectrum is quite uncertain. That's why I put this reference as what people commonly report for astrophysical backgrounds, but yeah.
Do I recall correctly, there is some kind of model-independent upper bound from astrophysics? And
so there are some works, there are some
claims.
Right,
yeah, there are claims of...
That's why this tension is kind of...
You're right, there are some claims of a model-independent upper bound. I don't know, based on interactions with astrophysics, I see a lot
Look,
of...
they got it to a factor of 2. Let's be reasonable. That's it. That's binary black holes.
So let me also say that, okay, for the sake of this talk, your conclusion is not exactly... but okay, I take it anyway. I'm just saying that, what was I going to say? That, of course, even, you know, they inferred the amplitude and slope, so the shape of this plot and the exact values, I think they may change with the future data releases. I wouldn't be 100% trusting these precise values that the collaborations are reporting, because there is a lot of modeling that enters in these posteriors. Lots of noise parameters that you have to marginalize over, so I would take it as evidence, partial evidence that there is a background, and then the precise value of the amplitude might be a bit lower or a bit larger, I don't know.
Also, what does one actually knows about the spectrum? Like here, its power law is assumed.
Right.
But is it kind of from the data?
So from the data, currently there is no strong evidence in favor of a deviation from a power law. So people have tried fitting, as I was mentioning, some broken power law with some breaking point at low frequencies that is motivated by astrophysics. But there is no strong evidence. So when they compare these models, there is no strong evidence for these extended models against a simple power law.
Can
so
it be
far.
something completely different from power law, or like this is
Like what?
no.
Like
I don't know, line. Can it be high?
well, typically, I will show you the typical spectrum from cosmology, from a cosmological background. It's a peaked spectrum typically, or power law, depending on which regime you are in. And from astrophysics, that's what people expect, right? People expect either a power law or a broken power law due to some of these environmental effects. So, yeah.
But you have the data points, right?
Yes, you do have. So you do have the timing delays, and then you can you can basically That's why I wanted to be a bit more precise here. I didn't call these really data points. These are not really data points. You see, these are already kind of posteriors for the amplitude of the timing delays. So there is already a fit here, which is done frequency by frequency, beam by beam. So in some sense, in each beam, you ask what is the amplitude that is observed independently. It's a free spectrum analysis, and then you get these posteriors. So, yeah. Yeah. Okay, so let me move on. Okay, this was just mentioning a bit how the astrophysical...
Sorry, can I show the plot again?
Yeah.
And there is a way I read it. So when this gray things, when they go down, that means basically it's considered, in those frequencies there is not much signal, right? So
you mean like the ones at high frequencies?
Right, yeah.
Indeed. In fact, in these plots, the lower bound on this thing is just a prior. So it's really cut in the analysis, it's really cut. One should never translate this directly into omega, because otherwise you would think there is evidence even at this high frequency. At this high frequency, there is no evidence. Okay. It's just really these first 5 beams, if you want.
it's 5, okay.
Yeah.
Mm-hmm.
Okay. So, yeah, I don't need to say much about binary black holes, because this talk will not be about astrophysics. But of course, the competing source for cosmology is this astrophysical background from supermassive black hole binaries. When they reach sub-parsec, even below 0.1 parsec distances, their evolution is driven purely by gravitational waves, and the merger is then, and then there is a merger that occurs. But this is the PTA, the region of the evolution that would be probed by Pulsar Timing Arrays. Again, the important message here is that the abundance of and the distribution of this object is very much unknown, And so astrophysicists are taking these observations, are giving them information to learn about these properties of binary black holes. But of course, there could be also a competing cosmological background. That's the idea. Now, this is a plot that we produce here with these collaborators for future sensitivities, but here what we wanted to stress, so these are all future interferometer, LISA, Einstein telescope, and this is SKA, so future updates of pulsar timing. Here what we wanted to stress, of course, is the presence of astrophysical background even for future sensitivities. These are backgrounds from either neutron star binaries or black hole binaries. And they will cut significantly in the sensitivity of these detectors. This is when we think about cosmological backgrounds, we should always keep in mind that there are competing astrophysical backgrounds. All right, so this serves as enough motivation to study. In order to understand whether a signal can be due to cosmology, we need to understand the amplitude of the cosmological signal, meaning this relation to the source and the particle physics parameters. We also would like to know the shape of the spectrum. Here there are two examples of cosmological sources which lead to very different shapes in the UV tail, if you want. And in some cases you have overlap with future sensitivities of other detectors, so you may hope to see these signals if they are of cosmological origins in other detectors. And then of course it would be nice to have also other signatures like the ones we were mentioning about delta N effective and so on. But these, of course, all these questions typically have model-dependent answers. Model, I mean particle physics, so source-dependent answers. So I will have to restrict, for the sake of this talk, to a specific type of source, which is actually a class of sources. It's not just one specific type. For this class of sources, one is able to make some more general statements. And these are what I will refer to as transients in cosmological history. So it doesn't mean transient in the sense of binary black holes that just give a transient signal in the detector. So the signal here is always a stochastic background, but they're transient in the sense that they're active at a definite time or epoch in their universe on a short time scale, and then basically they cease to be active. So the idea is you have a typical time scale T star, which is smaller than the Hubble time at a given temperature T star, and the source has a correlation length that is, by causality, smaller than the Hubble size, the size of the Hubble patch at that epoch T star. So that's kind of the picture. You have many sources inside one Hubble patch. The limiting case is the case in which the source fills up the whole Hubble patch, and that's when the correlation length is as large as the Hubble itself. So in particular, sources that do not enter in these categories are typically called long-lived. They may have correlations that are beyond the Hubble patch, for example, inflationary gravitational waves. There are cosmic streams also do not fit really into this picture because they're active for very long epoch. They keep generating gravitational waves for very long epoch, not at a definite temperature. So the typical example of this process is that we're all very familiar with, I mean, many of us for sure, is a first-order phase transition which proceeds via nucleation of bubbles. This would be a phenomenon that indeed sources gravitational waves. If this bubble expands, they will not, a single bubble itself will not generate a significant amount of gravitational waves, but upon collision with other bubbles and upon propagation on a thermal plasma, it would generate a significant amount of gravitational waves. That's a typical process that is studied a lot, especially in relation to the electroweak phase transition. Now, for these sources, the estimate that I presented in the very first slide is justified, and it goes as follows. Essentially, if you have a source that is active on a typical timescale T star, the frequency, of course, of the main harmonic is just estimated by the inverse timescale of the source, and that inverse timescale can be related to Hubble, of course, and then you get the following estimate, which is exactly what I presented at the beginning. So you have the nanohertz frequency range for temperatures slightly below the crossover, the QCD crossover, I mean, with an enhancement factor here, which is given by the timescale of the source. So if the source is active on timescales that are much smaller than Hubble at the crossover, then of course you would get a much higher frequency. Okay. So that's the first important message, if you're thinking about PTA frequencies for cosmology, is that really these observations are probing the epoch around the crossover. If you want to know about the amplitude of the signal, the amplitude, you can estimate it in many cases using the quadruple estimate. So here you just see the quadruple formula for the power in gravitational waves is the third time derivative of the quadruple moment squared. And basically, if you do a dimensional analysis estimate by just putting...
Sorry for interrupting.
Yes.
I'm a bit slow. So you're saying the size of this thing is just the inverse temperature, no? And the frequency is temperature.
Hubble, not temperature.
Why Hubble? Why not temperature? At the moment of
Why
nucleation, should not the local thermophysics...
So now you're thinking of, for example, of the bubbles.
Yeah,
Indeed,
exactly.
at the time of nucleation, now it depends a bit on the detailed properties of the transition, if it's super cooled or not, whatever.
I just want to understand the basics.
But
right?
typically
My
so-
proposal that it is inverse temperature does make sense.
Yeah, typically you're right that the typical size could be, but then if you want the typical, what matters is the typical separation, if you want, between different bubbles, and then
Because they will expand before colliding and producing waves.
But in any case, I think your remark is that, of course, let me see, is that here you can have, I mean, so in the case in which you have.
So here you are assuming that it is the size of the horizon.
Well, you see, there is this factor here that takes into account the fact that maybe it's much smaller than the horizon.
Which factor?
This factor here, t star to the -1 divided
Oh,
by
you
h.
keep it arbitrary.
Hmm?
You keep it arbitrary in this stuff.
Yes, for now I'm keeping
Ah,
arbitrary.
okay,
So
sorry.
if you want the logic here is the following: if you have something that is as large as the horizon, then you would give nanohertz frequencies for something that is around slightly below the crossover.
So the only thing you are saying here, it should be not larger than the horizon. True?
Yeah, it cannot be larger than the horizon.
Okay, you're right.
Yes, by causality, right? So if you look now at the amplitude, you can do what I was suggesting, namely a quadruple estimate, and you take all these length scales and time scales to be related. So you assume that the source is somewhat relativistic, and then the estimate goes through, and you get that the energy density in gravitational waves just goes like the square of the fraction of the energy density in the universe at that time that is in the source. So this rho s here is the energy density in the source, and this is the energy density of the background. So the amount of gravitational waves compared to radiation at the time of emission is suppressed by the fraction squared. Okay, and then it's also suppressed further by the time scale compared to Hubble squared. So these are both suppression factors in the amount of gravitational waves that you can generate from this type of sources. Let me express it in a nicer way here, where I already redshifted to today. You get an amplitude of 10 to the -8 when the fraction of the energy density of the universe in the source at the time of emission, this is alpha star, is of the order of 10%. And the time scale is comparable to Hubble. So this factor epsilon star contains these suppression factors, whether, the precise name calls the fact that maybe the source is much smaller than the Hubble, so there's many sources in one Hubble patch. This would be a suppression factor in the final amplitude of the signal. So by taking this formula and looking at the sensitivity curves, we reach the conclusion that for now and in the near future, by near I mean up to 10 years, we will be able to observe only things that make up at least 5% of the energy density of the universe at a given time, and they have a time scale that is quite comparable to Hubble, time scale and length scales. One should always think of time scales and length scales here. Things that have more, so a suppression here and a suppression here, we won't be able to see them in the near future. But of course, with future sensitivities, we might hope to see more things. So that's kind of the important takeaway here. The source should be relativistic, Hubble-sized, or roughly Hubble-sized, and it should make up a significant fraction of the energy density of the universe at that time. Now, in terms of the properties of the spectrum from these sources, one can think in this way. Of course, there will be high-frequency modes that probe the microphysical properties of the source just because of the wavelengths, and these will necessarily be model-dependent. So the shape of the spectrum in these frequencies will necessarily be model-dependent. In fact, it typically requires numerical simulations, as I will show. There are also modes for which one can make some more model-independent statement. These are modes that are super Hubble at the time when the source is active. Those modes cannot be too excited because of causality, and the slope of in this low frequency tail, in fact, will be also model-independent. it's just set by causality. Of course, many of you know already the answer to this, but there is an interesting twist which I will be talking about. So this is a typical shape of the spectrum from a cosmological source that is transient in cosmological history. You have a peaked spectrum, and then you have a high frequency tail that can be any of these shapes or whatever shape. It will depend exactly on the microphysics of the source, and again, typically has to be assessed via numerical simulations. And then there is a causality tail, how it's called, because it's made of super Hubble modes, and this is essentially set by causality. And it's model independent, roughly speaking, okay? Of course, you have to be, when it starts being model independent, at what distance from the peak, of course, that could be a bit slightly model dependent. So the interesting twist that I want to describe has precisely something to do with this causality tail. The common law that I think many of you and of us are familiar with is that this causality tail for these signals would go as f cube. It would grow as f cube. If you're not familiar with this, it doesn't matter because I will review briefly how the story goes. So again, this tail is made of modes that were super Hubble at the time when the gravitational wave source was active. So let's stare at the equation for the gravitational wave modes. This is the equation that one has to solve, and here I'm working with conformal time. So you see eta is conformal time, and this curly h is also conformal Hubble. So you have the equation of an oscillator which has a source which is just the anisotropic stress of the source. So if you focus on these modes that are super Hubble at the time h star, at the epoch h star, these have k much smaller than h star. The approximation that you can do is the following. You can think that you can approximate the source, the anisotropic stress, as follows. As a delta function in time, because I'm assuming that the time scale is much shorter than Hubble at a given epoch. And you can also assume the amplitude here, the space part, if you want, to be independent when you go to Fourier space, to be independent of k. Why? Because for these modes, the source essentially would look like something that is localized in a tiny region of space from the point of view of something that is much more extended. And then when you go to Fourier space, of course, you get something that is independent of k. So that's kind of the approximation that one can do in order to understand the slope. So you see there is no k dependency. The k dependence has been eliminated for these modes, at least at this level. Now, the initial condition is then independent of k for these super Hubble modes. But of course, you have to wait until the super Hubble modes re-enters the Hubble sphere. And once they re-enter, the time of re-entry is characterized by k equal to h. Once they re-enter, they will start just redshifting away. They oscillate just as an underdamped oscillator, and they just redshift away. So you get k dependence from the redshift factor here, because this a of the scale factor is evaluated at the time that depends on k, of course. Then you have oscillations. These oscillations will go away once you average when you compute the energy density. So now you want to know the energy density. So that's the solution roughly for h. All the k dependence is encoded in a. Now, once you look at the evolution, at the behavior of if you look at the behavior of this scale factor, you will notice that the scale factor, of course, the evolution will depend on the equation of state of the background. So in particular, the dependence is as follows. H will go like k to minus this power here of depends on w. And then from this, you can compute the energy density in gravitational waves, and you get this dependence here from k. So essentially, if you look at this exponent now, you reproduce the known result that for w equal 1/3, that is a purely radiation-dominated universe, you get a spectrum that goes like a cube. That's a standard result from causality. Of course, if the background was instead matter-dominated, here you would get a linear power, so it would be k. So it would be a sharply different prediction for the causality tail. But the point I want to make here is that actually the standard model at the frequencies that are relevant for pulsar timing arrays actually predicts a deviation from radiation domination. This we know because of the QCD crossover. Okay, in particular, around the QCD epoch, there are many degrees of freedom that become non-relativistic, and this leads to a sharp drop in the number of relativistic degrees of freedom. These are results taken from lattice QCD, where this lattice QCD calculation can can infer the values of the entropy and energy density degrees of freedom, G rho and GS. and you see they differ very slightly in this region, but actually this very slight difference is precisely what leads to an important deviation from radiation domination. Okay, so here you go from 80 degrees of freedom to, roughly speaking, 17, and then you go even below, of course, once the pions also become more relativistic. So intuitively, this is an intuitive explanation that is not totally correct. Intuitively, what happens is that you have many degrees of freedom that become non-relativistic, and since non-relativistic matter behaves as a pressureless species typically, what you can think of is that the equation of state would decrease from 1/3 towards 0. In fact, this is precisely what happens. But the more detailed computation that you have to do is really you need to infer this value of G star S and G star from the lattice, which lattice QCD people have done. And then from this, using thermodynamics, you just relate it to an equation of state. And this is what you get. The result is a deviation. So this is the equation of state as a function of temperature on the upper x-axis, which I then relate to frequency on the lower x-axis, using the usual procedure. So you see here that at very large temperatures above GV, in fact in the inset you see up to TeV, the equation of state is 1/3, as expected, is the one of radiation, but as you approach the crossover, there is a sharp drop, a 30% drop more or less in W, and then you go up again because of course all these non-relativistic matter that you have around is annihilating efficiently, and so basically you kind of hit back into the light degrees of freedom that remain below the crossover. So the message here is the following, that the causality tail, as we have just seen, in pure radiation domination would go like K cube. But due to a standard model prediction, so due to the QCD crossover, actually you see that the frequencies coincide very precisely with the frequencies where PTAs are observing. You actually get a deviation in the causality tail that is not just K cube, but it actually has a slight modulation at these frequencies. I don't know what happened. Let's go back. It didn't like the crossover apparently. Let's see what happened. I don't know, maybe it's just here. Okay, good. So that's what we noticed when with these collaborators at CERN at the time. So basically you have a larger amplitude than you would expect in the very low frequency tail, and you have this slight modulation induced by the standard model. Of course, in the so here there is a new physics wish, namely that you're wishing that there is a process that gives these gravitational waves. This has to be from new physics. But then once you have that, you get a standard model effect on top of that that can be nicely calculated.
Is this actually big enough to matter in like a real...
Right, great question. So we address this question by doing a fit to the data. So that's what I'm presenting here. Doesn't matter, these plots, I mean, it's very similar to the one I was showing before. But if you want the comparison that matters, I mean, typically in astrophysics, what people do is they compare bias factors between different models. And you see the bias factor for, so what you can look at is a comparison of a simple F cube, which is the standard prediction, to the standard model affected causality tail, and you get a log of the bias, log 10 of the bias factor of 1 for nanograph. So that's not particularly large, but it tells you already that it's what, according to some Jeffrey scale, it's considered substantially preferred. But again, it tells you that in principle the data is able to distinguish between these two models, which is what we wanted to conclude. What we hoped that we could conclude.
This effect that you are talking about, the very existence of QCD phase transition leaves an imprint on superhorizon modes, whatever, right? Now, in your case, the only problem is that the superhorizon that you are talking about most likely doesn't exist. But there are other superhorizon things which do exist. So this effect that QCD phase transition leaves a record in a spectrum of superhorizon modes.
Yes.
Is it something well known in cosmology?
So it is well studied, for example, in the case of, or well studied, I don't know how well studied, but it is understood in the case of curvature perturbation. I don't know if that's what you're referring to.
Something like that.
Right. So it is understood, for example, from the community that studies primordial black hole formation. This is very much studied in that community.
But again, primordial black holes don't exist.
No, but
in something which we can measure, can you see this effect? This is what I'm asking. Because QCD phase transition certainly did occur.
Yeah.
Did it leave an imprint in something which exists and can be observed?
So my understanding, I mean, I've seen these effects considered when people study the collapse of curvature perturbations in the early universe. But again, the consequence would be black holes, but only if you have a large amplitude. In that case, it can matter. But if you have a tiny amplitude like we observe from the CMB, then probably doesn't matter. So I don't know actually, because how do you probe the matter power spectrum at those epochs? That's the question if you want.
No, the superhorizon modes exist, and anyway, this is a separate.
Yeah.
Yeah, you should ignore this. Okay.
No, it's an interesting remark. I think
Okay.
maybe we can chat later,
Right.
more later about this. Okay. So so that's kind of the final statement from this part of the talk. Do I have more?
Yeah,
some
we
more?
got about 15 minutes.
15 minutes, great. So this allows me to go to one of my favorite topics, that is topological defects. And so these topological defects entered in, so for now I just try to describe some general properties of the gravitational wave spectrum for certain classes of models. Now I will specify even more to a specific type of source, which are topological defects. So why are these sources particularly motivated for near future observations? And again, we need to go back to these estimates that I presented at the beginning of the talk, that the source that we can observe should make a big fraction of the energy density of the universe, and it should have a size and a timescale that are comparable to Hubble. So in BSM, I can think of two possibilities that are well motivated. There are certainly others that can also be well motivated. I'm not claiming that these are the only two, but these are certainly two of the most interesting ones. I think we could agree on that. One is, again, first order phase transitions with bubble nucleation and plasma effects. However, this source has a problem from the point of view of observability, is that it's typically challenging to have Hubble-sized bubbles if you want to percolate at all, because of course in the limit in which this thing is really Hubble-sized, typically you do not percolate, okay? You do not complete the phase transition. So typically you have to go to some extreme regimes of these phase transitions, which is what's called, I mean, some classes of phase transitions are called supercooled, in which you can precisely hope to have these very large bubbles that would give you a very large signal. Instead, on the other hand, we'll see that domain walls, there's a particular type of topological defects, automatically satisfy this condition of being Hubble size, at least under the simplest assumptions for their evolution. And this is what I'm going to describe next. So I'm sure many of you are perfectly familiar with these objects, but I still want to give a very brief introduction for those of you that are not familiar with these objects in cosmology. So the idea is simply that I will describe this for the simplest theory that features these objects. You can think of more complicated setups where these objects would also arise. So the simplest, sorry, I might have been hiding all this part of the audience. Very sorry, I noticed just now. So the simplest model is the following: is the one in which you have a real scalar field phi with a Z2 symmetric potential. And now at high temperatures, what you typically get is a thermal mass for this field. So you get something that looks like this red curve here. It's a high temperature potential, but now as the temperature lowers, essentially you start noticing the low temperature potential. And the way this goes is known as Kibble mechanism. Basically, you can end up in one of the two minima randomly at each position in space due to thermal fluctuations, essentially. You can find also other types of models where it's not thermal fluctuations, but maybe something else that will also give a domain wall network, okay? But this is the simplest mechanism. And this mechanism, of course, of having fluctuations that allow you to populate the vacuum, or many vacua, is typical of topological defects. So it applies also to cosmic strings and monopoles and so on. So once the temperature is low enough, you populate this minima randomly, and you see here this is a picture would be picture in position space, where you can populate the minus or the plus minimum depending on the region. Now the boundaries between plus and minus will correspond to some localized energy density, which is roughly speaking two-dimensional, okay? So it will roughly be a two-dimensional distribution of energy density. That's why it's called the wall, of course. Now, the initial correlation length of this intricate network has to be smaller than Hubble by causality. Could in principle be as large as Hubble at a given time when this process happens. All right, so now this is actually the first kind of artistic picture, but it's actually not totally artistic in a sense. This is obtained by a simulation. So this is as realistic as it gets representation of what would happen in the early universe if such a scalar field with such a potential would exist. Okay? So an even more realistic picture, not in cosmology, you can get from condensed matter, as many of you are familiar with, but here this is really a slide of simulation. So basically, let me comment just briefly on how these pictures are obtained. They are obtained by simulating the classical field theory of this real scalar on a grid, on a three-dimensional box. And of course, you include the expansion of the universe. Here, it's crucial to include the expansion of the universe, otherwise you don't capture the basic properties of these objects. So the size of the Hubble patch at this time of the simulation is actually given by this small square, white square. Yes, by this small square here. And you see that in a typical simulation, at least at the beginning, we of course have many Hubble patches. And then as the simulation advances, the Hubble expands and eventually the simulation breaks down because you don't have more than one Hubble patch in your simulation. So what I'm showing here then it's a 2D slice, and in particular the contours correspond to the gradient energy density. Now gradient energy density captures approximately the location of the walls because this is precisely where there is more gradient in the field. So you see all sorts of weird shapes arising from the keyboard mechanism in this case. And the crucial properties of these objects these objects macroscopically can be described by two parameters. One, of course, is the tension. This is just the mass per unit surface, very much like the mass for a particle. And this will be estimated by the mass of the scalar times the Webb squared. So that's the first quantity. The other one is the width, which is often very tiny compared to the Hubble length. And so typically we think of these objects as being thin wall objects. You see, this is the field configuration phi that corresponds to the domain wall, interpolating between one minimum and the other minimum. And the width of this configuration is typically of the order of the inverse mass of the scalar field. So since these walls form precisely when Hubble is over the order mass, and then you follow the revolution for longer time scales, typically the width is very, very, very much smaller than the Hubble patch. And you can consider these as just two-dimensional objects, essentially. So for those of you that are more interested in particle physics, of course, there is a very important example in particle physics that is interesting, probably more interesting than the simple Z2 model I was showing, but I'm not sure. That is the complex scalar case, or also the axion case, as it's typically called. So let me just outline how the same thing happens for a complex scalar. So in the case of the complex scalar, what you have is the same type of Kibble-Zurek mechanism by which now you populate actually the circle here. And this leads to the formation of string-like defects. So the spontaneous breaking of a U1, of a global U1, leads to this formation of global cosmic strings. Now, when domain walls come in is if you give a mass to the Goldstone boson, which is precisely what happens in the case of the QCD axion. In the case of the QCD axion, the Goldstone boson gets a mass from the non-perturbative effects around the QCD crossover. And these effects, the potential that they give is a periodic potential. Here I'm showing one that has three distinct physical minima in the full axion periodicity. And so what happens again is since you're randomly distributed in this circle, you will randomly populate one, you will randomly go in one or the other minimum. And therefore you will also form domain walls. The crucial difference with respect to the simple Z2 model that I was showing before is that in this case you get a more complicated network where these walls are attached to the strings. And this is just due to the fact that, of course, as you go 2 pi around the string, as you go 2 pi in field space, so you go around the string, you necessarily have to cross domain walls, right? Because this is where the domain walls are localized, for example, at pi or depending on the specific model. So these are slides of by now old simulations where you see precisely that there are many walls. So these lines are the walls and they are connecting at a point, and the point is the string. If you want, there is a string that comes out of the blackboard, of the blackboard essentially. And you can see here there are many walls. They were simulating, people were of course here interested in the QCD axion, for example, DFSZ model The simplest one predicts NDW equals 6. This is just the number of walls that is attached to each strings. So that's precisely what they simulated. Okay. So that's just to say that the same phenomena happen in axion physics also, in particular in the QCD axion. All right, so the way that these networks evolved is very interesting, and it's called the scaling regime. They achieve a scaling regime, which is basically a balance between wanting to increase their energy density due to the fact that with the expansion more and more of these defects come into your Hubble patch, against the fact that there are interactions between these walls. So this is really just, one should think of this as a gas of topological objects that can interact. And so at the end, these two processes lead to the expectation that the energy density lead to the expectation that there should be a fixed number of Hubble-sized wall per Hubble patch at every epoch, which is very interesting. So if that's true, let's estimate the energy density in this fluid. Then it would be given just by the tension, the mass per unit surface, multiplied by the surface. And that's precisely here, that's the co-moving area in the wall. Then physical, you have to multiply by a square, and then you divide by the whole volume of the box. And then what you get is this. You get that all the time dependence of this energy density is encoded into h here, because sigma is energy dimension 3. And this quantity here should be approximately time independent, as I will show that this is true. So you see the expectation basically is that the typical time scale and length scale of this network of topological defects is precisely Hubble-sized. So at every time you're just dominated by one or few big Hubble-sized domain walls. Okay,
so obviously for string networks, people are very much disputing strings reaching a scaling regime. Presumably, the same people would argue that domain walls could also violate.
Well, there are some important differences between the dimensionality of the defect. So in any case, let me mention that in the case of strings, what people are debating about, to the best of my understanding, is not a total deviation from the scaling regime, but it's a log effect. So, you know, and these logs are peculiar of strings in some sense, because you know that the tension of a string is log divergent, global string is log divergent. So I'm not sure that all these discussions, how much of that would move on to domain walls, but in fact, your question is certainly very interesting, and that's why we had to do better simulations. Exactly, like these people have been discovering these things via numerical simulations. So that's what we are trying to do.
Sorry, but you say that the density in these walls is a significant fraction?
It can be a significant fraction.
And that doesn't disrupt the BAO or any other?
Right, so my focus here is things that happen in the very early universe before Big Bang nucleosynthesis, and then we will have to find a way to get rid of these objects way before Big Bang nucleosynthesis. So it will not impact cosmological observables like BAO or cosmic microwave background. Absolutely. Otherwise, of course, it would be ruled out by what's known as the Zeldovich bound, which is precisely coming from the logic you were mentioning. So again, here this is a slide of other simulations where you see that as the Hubble patch expands, the network simplifies, and you have these large Hubble-sized walls that extend over the whole Hubble patch. And again, these are all obtained by lattice classical field theory simulations. Now, this is what I promised, namely the fact that the network does reach a scaling regime. This is conformal time in the simulation. So you see there is a transient regime at the beginning of the simulation where this parameter is sort of time dependent, but then at the end it settles down to a constant value. Okay, so that's exactly the point. That's exactly showing that indeed the network achieves this scaling regime where there is one Hubble-sized wall per Hubble patch approximately. And now, of course, going back, relating to your question, this is of course a problem, because if you do have a fixed number of domain walls per Hubble patch at each epoch, then you simply get this prediction that the energy density in the walls grows rapidly compared to the background. In particular, it dilutes only as a to the minus 2 versus, of course, a to the minus 3 and a to the minus 4 for metal radiation. So this is what's known as this domain wall problem pointed out by Zeldovich already many decades ago. and basically rules out any spontaneous breaking of exact discrete symmetries in the early universe. Now, unless, of course, let me specify. Someone is calling? What's that?
You might be holding down something.
Huh?
It's an hour.
It's like the
Sounds
error,
like someone's on the
math error
keyboard.
sound.
Isn't that like an alarm clock? Time's up.
Could be the time's up. Okay, let me wrap up then. No, this is annoying though. But okay, well, okay.
Is it just this slide?
Yeah, it is. So I'll be very fast on this one. Well, now it's stopped. Anyway, so one certainly has to get rid of this issue, and the way one can get rid of this issue is the following. It's very easy, at least from this picture, is that basically you can assume that the symmetry is not exact. Okay, there is a slight bias between the two minima, and then if you have that, what happens is that initially you form the domain walls, very much as if this bias was not there. But then at some point, the acceleration due to this vacuum energy difference between the minima A and B beats the Hubble friction, and so at that point it becomes relevant for the evolution of the network. So this simple estimate, this simple logic would give you that when Hubble is comparable to the force delta V divided by the mass sigma for walls, basically you would expect this whole thing to disappear. And in this way, you would evade all these cosmological disasters. And actually, this is what we see in the simulation. So now I'm going to show an animation with the potential is a Z2 plus a perturbation, a small term with this Q is small, with a cubic bias between the minima. You could do also other types of biases, just an example. So you see in the simulation now the Hubble is expanding, and then you initially form this complicated network. This network keeps radiating a lot of scalar waves throughout its evolution, but especially at some point, all these walls start to shrink and disappear due to the effects of this pressure bias. So at the end, what's left over is just the preferred minimum, and you still have a lot of anisotropies here, homogeneities due to the previous existence of these walls. But if this occurs on sufficiently small scales, meaning sufficiently before BBN, all these things are thermalized, and you don't care much. In any case, you wouldn't be able to observe these small scales from the point of view of the metric power spectrum. All right, so this is just again a proof of what I was saying. Once you add this bias between the two minima, this area parameter, the number of walls, compared to scaling, the dashed curve is the one without the bias. When you introduce the bias, you see a very rapid decay to zero of this quantity, signaling that the network is indeed disappearing. Now, what we are most interested in, as I was mentioning, is the gravitational wave of these objects. Although there is a beautiful story about dark matter. In fact, you know that for QCD axion, this is believed to be the most important production mechanism in some QCD axion models. I don't have time to talk about that other part of the story. But from the point of view of gravitational waves, the estimate that people have been doing so far is very simple. People, of course, assume the standard picture that was showing in the first slides with the transient source, and then they assume that that these domain walls disappear at a given epoch with some instantaneous process due to this bias, and then they get the following. They get that the typical temperature of this annihilation is GeV scales, so the one you need to, if you're thinking of PTAs, for tensions that are around 10 to the 3 TeV, cube, of course, if you're thinking of the tension, and the bias that is around the crossover. So these things are interesting if you want to think about what kind of model building you have to do in order to fit PTA data. But otherwise, you can. I mean, I'm not only interested in that, and so you can take this estimate to be general, change the numbers to understand at what temperatures these objects would be active. The reason why the signal is dominated by the latest epoch, so the epoch of annihilation, is precisely that the energy density in this source grows rapidly compared to the background. So that's the fraction of the energy density in domain walls. It grows like a squared, so 1 over temperature squared, and this is due to precisely to the fact that the equational state of this gas is negative. Okay, so it grows very much more rapidly than matter. All right, so we in 2022 and nanograph then more recently in 2023 searched for these objects, and reported these posteriors. Of course, it's precisely what we were showing, namely that the fraction in this domain wall should be around 10%, so larger than 5%, around 10%, and then the temperature at which they annihilate should be around the crossover. Now, they also did some comparison with astrophysics, and with some astrophysical model that they considered, this model is favored, but of course, I take this with a huge grain of salt. I wouldn't even say that actually, because it depends a lot on what kind of astrophysical model you take.
Is the time scale over which the sort of collapse of the walls happens roughly 1 over delta V, or how big do I need to make delta V to get this to happen before BBN, for example? Like, how big does the bias have to
So
be?
if you want this kind of estimate, the answer is encoded here. So the delta V has to be, if you want to annihilate at 1 GV, it has to be GV for this value of the tension. If you put here 1 MeV, if you're worried about BBN, then you need to be sure, depends on the tension and on the
Sure.
It will depend on the tension, yes. All right, so now once you have, so what we added recently is the understanding that this, let me wrap up on this. So we added recently the understanding that, of course, this process is not instantaneous, and this leads to an interesting results in the gravitational wave signal. The process lasts for a while. So here the simulations is set such that the network should annihilate at time 14, but it actually keeps evolving for a while before it completely disappears. And this translates in terms of gravitational wave. This is omega gravitational wave, the time dependence of this quantity. It translates into the fact that the instantaneous annihilation approximation stops here, whereas actually the signal keeps growing for a while before stopping at a later time that is roughly a factor of 3 different. These things could only be encoded, could only be understood by doing an actual simulation. Now, the effect is very important because if you have a factor of 3 in time, means a factor of 3 in temperature. And the factor of 3 in temperature in terms of the amplitude of the signal, since the amplitude goes like the fraction squared and the fraction goes like t to the minus 2, it's a 4th power of temperature. So you get an amplitude that is 80 times larger or 100 times larger if you want, of the order 100 times larger than what you would have naively predicted. Okay, we also uncovered some properties of the spectrum. The probably is not really a single power law, but rather a broken power law in the UV, but let me skip the details of this. And let me also skip details of primordial black holes, and let me conclude. So I hope I managed to transmit the enthusiasm about stochastic gravitational backgrounds, but I'm sure here there is a lot of enthusiasm for that as well. And once, I think this provides, now that we have data on stochastic gravitational waves, what looks like a stochastic gravitational wave background, this also motivates detailed work about understanding the spectrum, amplitude, and shapes of these signals. In particular, this work includes also numerical simulations. For the low frequency tail of signals from transient sources, one can also do a standard model computation and finds that it corrects, interestingly, the spectrum. And for domain walls, well, I described basically how these objects arise, and I haven't discussed much about the other relics that one can get, but one can also get black hole relics from these objects and dark matter relics. All right, thanks. Sorry for going over.
By the way, if anyone needs to go, feel free. Otherwise, feel free to stay and we can ask Fabrizio some questions. So.